think it's going to be okay. Doesn't need to have. All right. That's good enough. All right, I can move on. No one should ever say that out loud. Oh, actually, it's still recording. That's good. That's great. That was recording. Me messing with this.
It's like real. It's more. You know,
It seems real.
Yeah.
It's got authenticity.
yeah. You don't want to be too polished.
No. God forbid. Okay, so what do you want to? Let's talk about what we've done so far. All right, so that's really easy to read. Hold that down for a second. So I've graded out what has happened in the past. What we're going to cover on the exam is everything up to chapter 4, right? So that's really position analysis and graphical synthesis. What we had. So we started out with mobility on the first day, just trying to think about like what are all the different ways this thing can move, or can it move? Actually, that's the question. You could have a mobility of 0, or you could have a mobility of -1. What do you think that means? It's locked. Well, that would be the 0. It would actually would be preloaded. There's a chance it has some stress built into the piece, right? Because like you'd have to actually kind of force it into to get into position.
Like if you were sitting on a tailgate and the linkage, is that like?
Not quite. No. It's more along the lines of like you could put something together, right? And now it's just fixed. But now if you have to stress it and then put the pin into there, right? That has to be some kind of preloaded to be able to put there. That's kind of the idea. We'll see one of the examples actually does come out to be -1. I haven't looked at those in a little while, so I actually should probably review like how that happens. It's possible. Okay, so then we did a 4-bar position analysis. That was really graphical, but we were looking at the Grashof, and we were also looking at the potential inversions that you could have of different, actually not just the 4-bar, but other kinds of mechanisms as well. We did inversions. And then, so we did the graphical position analysis. We did some graphical synthesis for a 4-bar and a quick return. And then we did some coupler curve stuff, looking at them. That was really more computer-aided things or looking up at different curves and trying to get them. We talked about the project. We included some static force, so I've included some additional static problems that we can work through. And then we also started trying to figure out the position analytical process. And that's really stuff that we need to really look in the book for. Some of them are can be quite long, so it could be sort of a pain. Along the way, things that we did that I haven't listed in here, we do want to be able to draw a kinematic diagram of something, right? To look at an object and then piece it to look and go, okay, yeah, here's what the essence of the thing is in terms of joints and linkages. And we also, I think it is, you should also think, I need to be able to identify what a vector loop is, and maybe even to write a basic vector loop equation. And I'll show you what I mean by that, okay? But then we didn't do anything in terms of the analytical synthesis, and we didn't obviously do anything with velocity yet. That will be stuff that's going to be after spring break. We are going to need to do some work with these, right? We just haven't done it because I've been putting it off so that we can finish the project right to there. So just so you know, the week or so after spring break, we're going to do some catching up in terms of some work. Well, I'll try to figure out a way to balance it so it isn't like an overwhelming amount, but I honestly believe we don't learn anything unless you do some work on it, so some practice. So I'll be trying to figure out what that's going to be able to make it so it's something useful. And of course, this exam can float around there, but typically, I don't think we can really do analytical synthesis on an exam, but we will have velocity and acceleration, and cams will be on this exam right here. Well, actually, cams might not be. There might just be velocity and acceleration stuff on there, and some of the stuff that came before too, right? It's a what do you call it? Cumulative, I guess you could say. On the this was what I had at Coast Guard. Was just listing down various things. I don't know, there's way too many topics up there to read them all off, but something that you should consider when you're doing any exam is to go backwards and think, okay, here are the possible topics that we've covered. And even though I've given you practice problems and I've given you an old exam, just remember things that we did in homework are also that aren't necessarily represented here are still part of things that can be testable. Okay. That's not meant to be saying, hey, this is all you need to know. So if after the exam you go like, well, this wasn't one of the practice problems, I'm like, practice problems are there to help you. It wasn't to be, this is all you need to know kind of thing. So what would you like to cover? This is your time. Some of these are easier than others, so maybe you don't want to look at the thing, look at every single one of them. I know that statics, I've worked through a bunch of the statics problems. I gave you I purposely found ones where there were answers in the back of the book from other different statics books, but I don't really have, for many of them, I don't have the solution manual. But I can work through some, but I don't want to really actually give you all the solutions to those. I really want you to really try on them yourselves and get better at it. So what would you like to cover? Anyone speak up?
I just had a question about the 4-bar, like in the homework, the one with the football kicking.
Yep.
So I understand how to make it, but I don't understand how to tell which way is like the quick part.
Oh, okay, so I have to really kind of work, get my brain worked around to the thing to try to think about which direction the thing's going to go. And mostly it's the one that's the shorter sweep of the arc. If you take a look at the crank, right? If you take a look at what it's going through, because it isn't like 180 and 180, it's going to be smaller on one side than it's going to be on the other. The one that's smaller, right, is going to be the one that makes the thing go fast, right? Because so in order for it to that is the quick part of it. So the name, the quick return, all depends on which direction you're rotating it, right?
So like on the sketch here, like it's shorter here, so it's quicker this way.
It's actually this guy here. Like you might want to draw where, draw where this thing extends to, so you can see okay, it goes between here and onto the other piece. I think that's how I would say it.
This part is shorter than.
No. Okay, I'm trying to think how to say this. Let me look at let me pull up the blackboard and go to that one. Go to the posted solution for it. It's an exciting video so far. It's going to get an Oscar. What the hell happened? Where's this going to go? How does it? I can't see on this. I can't see on blackboard. Where is the thing over to the left? A student showed me once.
Go to the 3 dots in the upper right-hand corner.
Yeah.
And then zoom out a little bit.
You think?
Yeah.
Oh, wow.
And then click on the blue thing.
Wow. Why did that happen? Must be weird. Okay. Homework solutions. What homework was this? 2?
3.
Three. All right, so it's trying to think how to say this. Here is where this extreme position right here, right? So trying to see how to say this. Excuse me. Okay, so when these two things are in line with each other, when the crank is in line, is overlapped, I should say that, is right here, right? But when the thing is extended, its full reach is right here, right? So those are the two extreme positions where in between the crank and the coupler onto the thing. So the arc between these two is shorter over here than it is to there, and that's the thing that's making it a quick return. So let me think, as I'm thinking about this, right? So it makes a faster journey in this spot than it does over to here, or obviously the crank should be rotating at a constant RPM right there. So its motion between this and here is going to be the faster of the two. So if it's rotating, let's say, I'm trying to think now which direction the thing's going to move. If this is moving clockwise, it's going to return in this direction. This thing is going to start moving backwards, right? And it's going to take a longer arc to get back to that position, so it's going to be slower. So when it comes forward between this way, which is now going to be the thing that makes it come down this right here into this position, it's going to be fast. Does that make sense? And truth be told, I probably would get it backwards. Probably 50% of the time, and then and then have to check it, right? So as being something as a exam problem, I wouldn't necessarily go, oh, you need to be able to recognize this, because I wouldn't be able to do it myself. I probably would overthink the thing and get it backwards each time. But I would try the thing out myself. Try it both ways and see what the result was going to be. Does that make sense? I don't know if that's a fair thing, that I'm not quite have my brain organized enough to be able to think that through every time. But that's the concept.
So as I was looking at this, I was trying to go through the steps of getting to the quick return, and so I got confused. So once you find where the midpoints intersect and you find that point, and then you connect the two linkages to that point.
Okay.
How are the circles that you draw? I don't know the word I'm looking for, but they're just random, right?
Not random necessarily. Okay, so I know there's lots of mess going on right here, but once we found where that point was going to be, right? Because we were given this, and we were given this, and we were able to, based on these lines right here, right? I'm just walking through this right here. Be able to find that these intersected at a given point right here. We were able to identify that this right here was one of the legs, and then what was the leg, and here was the second position that it would be in. Now we want to have attachment points. This is going to be a single attachment point. Well, that attachment point will be right here based on an arc that we draw with a compass. Now we want to try to figure out a location for a crank. If this was a non-quick return, there would be a line that would be drawn right through this. and then a crank would be put right here.
Okay.
Okay, so, but for a non-quick return, we need to find some type of wedge, right? You can imagine that any place that we stick, okay, so here's an arbitrary one that we would place on top of here, an arbitrary location that we were doing. We know at this arbitrary location that the linkages will be, a part of the coupler will be right here. And then part of the coupler will be right there, right? This will be the extended part where the crank and the coupler need to be extended to right here, and then the crank and the coupler need to be overlapping up here to be able to achieve this. This angle right there is going to decide the nature of the quick return. Right, so we do that calculation ahead of time that it needs to be this angle, and then graphically we just have to kind of do our best to try to figure out how do I make an arc, an angle right here. We could do it in SolidWorks. We could just assign that angle and make sure the rest of the stuff is is like it's attached at these points, and we can start moving this thing around. And you can see that it's kind of constrained, that there's only so many places that you could put it. If you put it too close down to here, it's not going to have the crank and the coupler would end up being a non-Grashof thing, right? It's just not, the shorter one of them is going to be way too short, so it wouldn't be able to make a full rotation. So there are some limitations, but otherwise, it's really just trying to force that angle to be in there because you want a particular quick time.
Okay.
Does that make sense?
Yeah.
Okay. I do have problems. The problems, obviously, that I've posted some of the solutions to on here, but we can work through them. Do you want to do a statics one, or what do you want to go to? Some of them, you could work them out yourself right here. This one, I think I give you the solution to it. You can just beat your head into the ground. But since I have it up here, I'll quickly do this for the mobility. I think I posted what the answers are here at the back of the thing on this one, right? That this was a -1. So this is one that could potentially be like if you would have to, all the linkages would have to be the perfect exact length to be able to assemble this. And if they're just a little short, you'd have to put a preload onto the thing. That's the idea, where you'd have like a -1. But as part of this, let's see, I said that there are 10 links and 14 joints. So going through my, it's important to make sure that we're, see, kinematic fundamentals, and we go to mobility, and this is the, sometimes, what do we refer to this guy as? Yeah, the Grubler's equation, but actually we're using the, I think, Kutzbuzz thing, yeah. So we're always writing out M is equal to 3L minus 1 minus 2 J1 minus J2. And the important thing to attempt to do is to identify what kinds of joints these are, and also be able to pick out all of the links part of here. So we'll start with the ground link is always 1. So this is the same one. These are all 1. We don't have to, it's not multiple things. So we go 2, 3, go to 4, 5, and 6, 7, 8, 9, and 10. You agree with that? And then for what did I decide to do? I guess I decided. All right, so we have to remember that this, when you have a joint that has multiple links attached to it, that actually counts as you could either count it as 2 J1s or 1 J2. But I think in the book they decided to call this this one actually counts as two J2s. And because this has connects actually 3 links here, this is also a 2, and this is also a 2, and this is also a 2, right? So each of these counts as 2 joints. And so we have a 1 here, a 1 here, a 1 here, 1 here, 1 here, and 1 here. That's how I've written it down onto here. I think I was coming up with my own method of doing it here. So, is that true? Yeah, so we say that this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you go, M is 3 times 10 minus 1 minus 2 times 14 minus 0. And then what we end up with is a negative 1 as part of that. And you can kind of almost, maybe you can kind of almost see it. I think I'd actually want to build it in SolidWorks to kind of convince myself that it was that it was a preloaded thing. I know, I'm just not trusting, but it's an interesting observation to make that you could draw out something and then suddenly realize, well, wow, this thing can't even move. Not only can it not move, but it also would have to be preloaded to be able to exist. And this one is kind of straightforward. It's the mobility is quite often for a lot of the problems when I just pick them out of books. The mobility ends up being 1, like a lot. It's hard to actually most of the books that I'm drawing things through. And what's really kind of something I should emphasize maybe more in class is that I'm looking at lots and lots and lots of books. That I mean, it's funny how I just keep finding more and more mechanisms books, and they all have like a ton of different things that they emphasize and different techniques and things. So I'm just trying to sift through kind of what's the best approach. I decided to stick to this one. But one of the for everybody, the first thing they do is this mobility. The next thing they do is the Grashof thing. So that's the reason why some of the logic of what I've decided to start with where we're trying to organize the thing. There probably will be one of these questions, by the way, because it's an easy question to ask, and it is like the first thing everybody asks. So presumably it's a fundamental thing everyone wants you to know in mechanisms. In this one, we have the ground link 1, and then let's see. We can say that this is. I'll try to organize my thoughts here. I'll make sure I'm not going to skip one. 2, this is a 3, we'll call this guy 4, and that's 5. Did I get all of them? I said there's 6. What am I missing? Who am I missing? This guy. And then I think all of these are single joints. Yeah, there's nobody here that's double dipping, even though that's like in the middle of the thing. It still counts as just one joint right here. Got it. Let's see if I got it. 1, 2, 3, 4. I lost track. 1, 2, 3, 4, 5, 6, 7. Did I get 7? I got 7. Okay. So the number of links is 6. The number of joints is 7. Therefore, our mobility in the equation is going to be, what do we say the equation is? 3L minus 1 minus 2J1 minus J2. Put that in there, and we get, so what is that? 15 minus 14, yay, it's a 1. And remember what that means? Why we would do this?
degree.
It helps to figure out the degrees of freedom.
Yeah, so it only has 1 degree of freedom. You move any particular thing, and there's only going to be like one motion that's possible. So what would it mean if it was 2? What would that kind of tell us? It means we need to have 2 inputs to be able to have a desired output, right? For instance, that would be like maybe those would be actuators. Maybe there would be 2 different stepper motors that we would be putting in there in a control system to be able to have, right? And then the idea moves on and on and on, right? So you have like a 6 degree of freedom robotic arm. You need 6 actuators to be able to get it to move the place that you want to move it. And the benefit of doing mechanisms versus robotics in that sense, right, that generalized thing is you don't necessarily need to have that amount of motion, or that complexity if you're going to make the same repeated motion over and over again, and the expense and potential for things breaking. So you still want to be able to, even though we have, the sophisticated computers and things that can make the motion in an infinitely controlled robotic arm, if you want some precision and repeatability and that kind of thing, you can make a mechanism that's constrained so it only has 1 degree of freedom, and now you know it's always going to make that motion. And I would like to see a mechanism that looks like this and find out what it was for. But I'm sure it's got something going on here. So this is like one that's got like all the kitchen sinks. The kitchen sink? Yeah, I think so. So when we go here, we have we call that joint 1. This is 2. And 3. No, I said joint link. Link 1, link 2, link 3. Here's link 4. I decided it was 5. This is considered a link. That's 6. That's not necessarily obvious. This is link 7. And this doohickey thing is link 8. Now we have a lot of things that they end up calling half joints. I think they're calling, I get this backwards. It's weird how they decide that one thing is a half joint. Yeah, something is a half joint, but it counts for 2 things, right? There are no rolled slide half joints in that one, but this one has, so we have to be careful of multiple joints and what's called half joints, right, onto things. And yeah. So this guy right here, he's a single joint. Here's a single. I accidentally wrote 2. I meant for 1. The numbers inside the circles I'm trying to represent as being the order of the joint, right? So here, this is actually 3 links coming together. So it actually counts as having as a more complex joint, which has the stupid name of a half joint, right? But or the order of the joint. This right here is just a single joint that it can move about. Here is a single joint that can move about. This too is considered a single joint. Now, most of the time we're doing revolving or revolute kind of joints, right? But also sliding is a kind of joint. And because it can not only, like, if this thing had, I'm trying to think, if there was something that was forcing this thing to always be in contact with this, I think, is that right? Yeah. Anyway, this can slide, but it can also roll, right? It can also pivot at that point.
Is the most something can be 2? Like if it had 4 links connecting it at one point?
Gosh, I don't know the answer to that. I don't know. I'd have to see. I think it's only the most it could be is 2.
Okay.
I think it's the half joint principle onto the thing. I'd have to read just a little bit more closely, but that's a good question. I don't know off the top of my head. So anyway, this is a complex joint right there. And this is a simple joint. Here's another simple joint. This right here, this can slide and it can roll. So it's a complex joint. So let's see if I got this correct. First off, I ended up with 8 links. Did I do that correctly? Yes. L is equal to 8. And then I said, how many J1s do I have? Okay, so the thing that I'm doing right here is I don't know if I should have called this a 2 in the same way that this is a 2. Right here, this should count as 2 joints, right? So let me clarify this. I was playing an audible right here. I want to double check something. The equation I want to use is this guy right here, right? Minus 2J1 minus J2. I think, am I correct if I say that I could either count this as 2 J1s or 1 J2 and it'll be the same thing? Yes. Okay. So I have that freedom right here. I think technically in the book, when they mention when you have multiple links coming to a joint that you need to count them twice as J1s. So maybe that's the thing that we want to try to do, because I don't know the answer to your question. Right, I need to look in the book. So we'll count this twice right here in the event, because I think that's what their instruction is in doing there, is to count this thing twice as 2 joints instead of calling it a half joint, even though you would end up with the same thing. So if we add up all of the non-half joints, the full joints go 1, 2, 3, 4, 5, 6, 7, 8, 9 J1s. And then we have 1, 2 J2s. And if we put this together here, so we're going to have, so what's that? It ends up being 21 and minus 19, 18, 21 minus 18, and then, yeah, so 21 minus 18 minus 2 ends up being 1. So this ends up having 1 degree of freedom that you would never know. So apparently you can turn this crank and everything will move in a particular orientation. I do believe that there needs to be something here that makes sure that doesn't come off of the surface, though, right? That there is a element to that. I think you can handle the Grashoffs. You know the answers to these are here. Here is our design problem here. So here's a graphical synthesis problem. I think there are two solutions to this, right? Well, for one thing, I think when I looked at this later, I was like, if I'm going to, if this was going to be a non-quick return thing, I end up actually going off the side of the paper. Like I said, I didn't really pick a good spot to put this thing onto the page. That is my recollection. Does anybody have any requests or anything that you want to do? Just want me to walk through the thing. You have the solutions to these, right? Yeah. So, but I'll walk through it. I remember this was like 5 years ago that I was creating these things. So I was making this class. I was like, I want to give people practice problems. So I was writing an exam and writing old exams, fake old exams. So anyway, the idea here is right? We want to connect the dots. I might want to make this whole thing smaller, just in case it doesn't get in the right spot. Oops. So there. Oops. Okay. All right. So I connect B to B. I connect A to A. I used my extremely disappointing whiteboard compass. I was so excited when I found this thing. It does not work nearly as well as I imagined. I made my own at one point with a couple of rulers and a pencil onto the side of the thing, and then I used one of those little clippies that you use to put paper together. And I think it actually works better than this thing. See if I can do this. So, this is another thing. Let's do that one first. Now, I think it's going to be up on the upper part of this. Wait, that didn't look right. No, I messed that up. Didn't I? All right. Okay. Right here and here, and I want to come to this guy instead. Here and here. That worked out pretty well. And that should be a line that's through the center and perpendicular right here, right? And now I want to do this one. It's almost better to use another color. Maybe what I'll do is, I would appreciate if you didn't erase yours on your page, but maybe make them like really light so it doesn't get too confusing for you. So I just want to see that if you made a mistake, I want to see how it worked out. So I guess actually, am I still using the same font? I guess yeah, I guess come over there. Oops. Did I do that correct? Performance art. And here to here, it looks about right, I think. There. Boom. And now we have a mechanism or a piece right here so we can get the joint flow. So I did it onto there. No, I decided on here. I decided to make it from here to here, built it off of this. I don't think in my instructions did I make it clear that it could go the other way. And then And now I want to make the connection points to this. And I have some freedom, unfortunately, like to how big I make this arc right here, right? So it could be all the way out to there, or it could be like really, really, really close. Probably want to make something, this is part of the synthesis thing. There's no one answer. Shanice. Oh, okay. She was first.
Is it supposed to be at the intersection of the two midpoints? Like the lines that you connect?
Oh, you know what? You're right. I just messed it up. Sorry. My head's out of it. Sorry. I messed up. I apologize. That was good. Thank you for catching me on that. To there. So, like I was saying before, yeah. And I chose that randomly. But now, that's going to be these are the spots right here. Now we want to choose this. So if it's non-quick return, we need a better name for that. It's going to land on this line, the ground for the driver. Now, because remember that these things we're all drawing it in one plane right here, but it's a three-dimensional thing. We could put it down here too. Right? It would make the crowded picture onto the thing, but the other thing could be over to the side or into the front of the thing that's driving it, so it could overlap it.
So it doesn't matter if you put the leg on A, going from A or to B, doesn't matter?
No, it really did function as to what the purpose of the thing was going to be. Like for ours, we wanted to make it look like it was a kicker, right? It looked like a shoe. So it connected at the ankle instead of at the toe. But could be something like a blade or something right here that we're stabbing something into. I don't know what this thing does. But by the way, there was a interesting opportunity to make use of this for one of the sophomores in their design thing. What is that called? Analysis by design? Or was it something by design? Engineering by design. Why I can't remember the word engineering. They wanted to. They came to me. Said that somebody referred them to me. Said they wanted to make a solar panel move along with the sun, right? To moving from one spot to another. And I was like, he said, I came to him and said, wanted to have a cam. I said, I want to design a cam that does you want a cam? You want a 4-bar, right? So we could make so there's an opportunity, right? So if you could picture this upside down now, right? You could make the thing and rotate it with I'm just thinking, it's an application because it seems like you see these things and you don't think, well, what the hell would I ever use this for? So anyway, we could pick it at any spot that we want. And that'll decide how long the coupler is going to be, but the crank has to be 1/2 the distance right here, which we already have the middle of this right here. So we can do our very best, and this gets a little difficult because some compasses are very difficult to use when you want to make a small, on the small side of, so I chose this point right here, but, yeah, this point's random. Yeah. But you can't choose a bad point, right? As you get to closer and closer to here, you're making it a chance there's not Grashof. Because of this length right here, and also the ground link is being decided right here. So if we were writing a computer code for it, we might write the equations that for the thing and make sure that we weren't like accidentally picking something that's too short. But graphically, we could probably just try to maybe have a little bit of trial and error. So we want to definitely check for the Grashof part of this, and this is going to be a terrible circle. I don't know if I should blame the equipment or operator error. Yeah, see, it's because it's shifting over. I got to be careful to keep it in one spot. Yeah. So that's the best that I can do right now in these circumstances. So what we find is this is we could say this is the actually most of the time I end up drawing it extended here. So here is the crank. And then here is, in red, the coupler. So this is the extended position of this. And then the next thing that I need to do is check it for Grashof, right? So, and maybe I'll draw in here what the ground link is going to be. Right, so that would form a 4-bar right here. So based on my ruler right here, I get this one is going to be, I'm going to call it 15. It's like 15 and a half. It's easier to math. And so the crank that I have right here is about 5. The coupler is about 13, and then the, we'll call this 6. So the longest is going to be 15, and the shortest is going to be 5, so that's 20. The other two, the P and the Q, no matter which one we have, are going to be 13 and 6, right? Did I do that right? 13, 6, right? So that's going to be 19. So this is, I chose poorly. This is non-Grashof, isn't it? Or is that, let me double check. I just confused myself. I have to recheck these things. Well, I told this book, right? Like, is Grashof, the case of Grashof that I just forgot? Anybody remember off the top of their head?
The case of Grashof, S plus L is less than or equal to B plus B.
S plus L is less than or equal.
Yeah. Okay, so that when it's Grashof. So this, you're all agreed this is non-Grashof? Because yeah. Okay, just double checking. All right, here I don't have it off the. I don't like to rely on my memory onto these things. Yeah, S and L need to be less than P and Q. So this is a non-Grashof. So I chose this part right here poorly. I could probably, as I move the thing outwards, I could now like get the coupler needs to be longer. And I guess I could kind of like see this, or I could actually choose this to be a longer. Those were the two random choices that I had, right? In terms of the synthesis. One of the choices I made was that I was going to make it a non-quick return, but then after that, all the choices that were left to me was how big I made this arc right here and how far along here I made that.
Can we do this problem with quick return?
Yes, I do have it. I think I had a problem. Maybe not. It said design something for a quick return. That was actually a hard problem. Okay. I can attempt it. what quick return do we want? I think the 0.15 is the easiest of the quick returns to try to do. Okay, so all of that is the same. But now we want to do a quick return, and the time ratio, well, we want to find what the time ratio is. Okay, so here's one where we have a 1 to 1.15 is the quick return thing that we end up having. And so when we do that for a quick return, whereabouts in the book is a quick return? Is that in chapter 3, or did we jump to chapter 4 when it was really introduced? I think it's chapter 3. I want to find the equations that we would use. So here's what, when in doubt, I'll look for the index here.
Page 117, I think.
117.
18 is the equation.
Okay. Yeah. Okay. So we have a time ratio of 1 over 1.15, and that's going to equal the alpha over a beta, which we also know is going to be equal to alpha over 360 degrees minus alpha. So what I'm able to find from this is that I get an alpha of 167.4 degrees. And the really important thing that I want out of that is to get this delta, baby delta, of, we take 180 and we subtract the alpha. So as part of that, I get 12.56. which is sort of an obnoxious thing to have to do by hand. This is 30, right? And do I have it with me? Oh, yeah, I do. And I can also have my protractor as part of that. And so what I want to kind of do here for the quick return, I'm trying to remember the process here. Well, for one thing, I didn't do myself any favors by making this arc as small. So maybe I want to like expand that out. So it gives me a little bit more room to work with in terms of the narrowness of how far I can make this thing out from each other. So I will not make it the full depth right here, but come to right there. Hopefully I can do this. And I'll make those connections, and this would be the dash. That would be the spot where it would be a non-quick return. So what I want to do now is I can randomly pick a point here and then hope that I have one over this way right here. Or I can like maybe pick a spot over here. Maybe I could try to see if this is possible, right? That I could. So let me experiment and see if I could make it so it's, no, that's not going to work. Yeah. I'm going to go ahead and pick right here because it's kind of tough to do this. But I think it's easier to do it on a page. And I can see, now I can start to try to pick somewhere along here where I'm going to get that line. So, let's see. It needs to be at the center, isn't it? Yeah, so I want like 12 degrees. I think it is. I'm doing this the wrong way. It needs to be that way, right there. So I need to, yeah. How am I doing that? So, yeah. There. So, is that all right? No, I need to have this hooked up here. That's where it's from. Okay. So, I need to find a spot. Yep. Yeah, there you go. I think that's going to be right. Yeah, this is a really unfortunate location onto this one. I think I have to keep coming up to right here. No, it's just as poorly planned out. Yeah, I think the spot that it would have to attach is like up here, and still it's like I'm like at 20 degrees onto the piece. So this is like a sort of a challenging one to do, and not necessarily something that I would do without like planning out ahead of time that I had enough space to be able to put the thing. But you get the idea that I have to make the angle between here and there has to be 12.56 degrees.
So the angle between the arbitrary point.
The arbitrary
point.
Yeah, this line that I had picked right in there.
Okay, and the point that you need to get to. Okay.
So when you do that arc, the purple one?
Okay.
Yeah, that one. So you connected the line, that dashed line to there, right?
Mm-hmm.
And then we're forcing the angle between that one and your arbitrary point?
Yeah, I drew this line arbitrarily.
Okay.
Right, and I could have made it up here. I could have put it over to there. I was trying to figure out a place where I could like come off of this thing, and then I should have maybe measured it down this way to be able to like find where the spot is going to be. Right, so I need to maybe connect this thing right to there at where 12 is, and then to slide it up to. Yeah, once again, it needs to be like right into there, right? So now, from here, that has to land on this line, and then now my ruler needs to be right. And then once again, the thing's only like on 15, right there. This is like probably closer to where it needs to be. Where that's close to being to 12, and this is the intersection, and it needs to land on this line, and then this thing needs to come here. So right up here would be the place where we would need to put it. Does that make sense?
Yes.
Yeah. But it needs to be planned out so that it's actually possible to do on the page.
So now the crank length. You draw an arc out from that point to the lower, like the extended point?
Let me think. I still think it needs to be. Oh yeah, I need to look at this part in the book right there because. What you need to do for that, it's hard to do this without showing you the slide from which we got this topic. Anybody remember what class that was? Was it class 3, class 4? I just looked at class 3. All right, so I always go right. I have to erase this. Yeah, this is. I have to go back to this each time. Right here is where we find the length, right here, right? So we have to draw out this line right here, and then draw out a compass and figure out what that difference is right there, and half of that distance is going to be our crank length. Okay. We extend out. We see the spot where we're going to. Here's the fully extended length, right, of our coupler and our crank. Our coupler only goes to. Our crank only goes to this far, and that's going to be the length of our coupler, right? But here is going to be the overlap condition. So we want to take that overlap condition and the fully extended position. We take the fully presented and take a compass and make an arc right here. That right there is the del that we made, right? We made that del in between there, so to make it the quick return that we calculated over here. But we take this arc and we draw it between here, and then we measure out what this length is. We extend from this, and we see that that's going to be twice what the crank needs to be. So then we're able to pick out the crank length onto the thing. And then the coupler is decided by that. Does that make sense? No. Shanice, doesn't make sense? Well, I mean, we know what this distance has to be, right? The crank and the coupler, this point got decided, right, for us already, right? Because of this angle right there. There was some amount of freedom. We could have moved this thing down here, and then based on, and then it would have been decided where this location was by maintaining that angle, right? So there was some amount of choice that we could make, right? There was a limited thing. It would move this piece up in there. Much easier to do in SolidWorks when you make that angle and define those things. But once we got to this right here, this is what the coupler and the crank and the coupler need to be this length right here. So if that's true, we can just go ahead and take our compass and go, all right, so at this position right here, the crank and the coupler need to be this length right here. Well, actually, the coupler minus the crank need to be this length. So, like here is the coupler, here's the crank in this position, here's the crank in that position. I guess I'll teal tone. And then here's the coupler in the extended position, here's the coupler in the overlap position. I'm drawing them side by side, but they're overlapped with each other, right? So in order for that to happen, right, for this length to be possible and that length to be possible, this crank needs to be 1/2 of that length. Does that make it clear? All right. I found this one in a book. I thought it was kind of an interesting position thing, because I could, once again, here was an application where you could kind of like imagine, like, okay, we wanted a door to be able to be stowed away in one position here and then make a linkage so that the thing kind of like swung out of the way. So in going through our methodology onto the thing, we can connect and say, okay, well, we want to make B1 to B1 right here. Oh, come on. And A1 to A2 here. And I think my compass isn't going to be big enough to be able to do this. So we might have to do some approximations as part of that. Let's see if I can have something to look at while I'm doing this. Double check. Yeah, here you go. Well, that's exam 2. Would not tell me. No. Well, that's exam 2. Okay, here it is. Okay, so what I want to try to do as best I can is to draw out an arc. An arc. Let's see if it's going to let me. Let's see. I have to do it again. Let's see. Oh, I need to go over that one. Right? Didn't quite make it. And I'm not actually sure which side would have been the better side to make the mechanism. Probably onto this side over here. Try to make it something over there. And then try a similar thing here. Oops. I really screwed that up. Double check that. Oh, that was supposed to be right there. This was supposed to be. Yeah. So this one really should be pretty horizontal. So okay. My bad. Wasn't looking at the big picture. Be nice to put our links onto here. Put our grounds onto there. So I drew those things out extended, but really over here, yeah. It'd be nice to put them on that wall. So maybe, and maybe make a little tab onto the thing, right? So once we've located those points, we can get rid of a lot of things that aren't necessary here. And I'm not erasing them all the way here, but kind of getting them so they don't distract us too much. So now, as part of this, it's really, well, how the hell are we going to connect this? There's nothing that says a link has to be a straight line, right? A link could be any shape you want it to be. You know, a link could be that right there, right? That knowledge of that can make it so that you could make a mechanism that's possible right here. For one thing, this is the ground that A needs to go to. So we can have a bar that looks like that right there. Right? And we can have a bar that looks like this right here. I'm just giving you an example of something that could be done, right? And then when it's in the stowed position over here, it might look, I'd have to use my imagination to say, and by the way, this actually, that corner right there might bounce into this. So we might have to be like a little bit more careful and in the way that we design the thing. We might actually, whoops, I just marked myself. Maybe come out like this right here for the bar. And maybe like it looks like, it has to look like something like this. So that when it comes out into the stowed position, and this might be hovering over the top of the door, right? So it might not be possible to, in this configuration, to make it so that like this is attached to the side of the door. It might need to be above the door as part of this mechanism to bring the thing out over to the side. It's just demonstrating that like a couple things that we haven't covered really, that there are other, you know, considerations to make, but there are other choices that are available to us to try to accomplish the task.
So like the limiting factor here is the wall there, so you can't have one ground, you have to have the two?
I think it has to land on that line.
Yeah, but I'm like, normally we would go to the intersection and put like one ground there.
Yeah. If it was that was like one of our choices. That's one of the kinds of lots of times that would be like maybe one of the rocker design. Like if we, you know, when we wanted, this would be more like this is a 4-bar design where we're actually where the door is the coupler, right? We could also make it so that we could choose one of the links to be, I'm trying to think. I don't know if we could do this, what you're referring to, which is usually going to make the rocker design. Usually that's where we have the intersection between the two things, where we're going to pick one of the legs to be, you know, like to be the main focus of the thing that's making the swing back and forth. I don't think this one's actually would be possible for that design. This is trying to make a 4-bar, which, you know, like trying to not make it as ugly as that looking thing right there. I think I just did it again. Maybe just as ugly. Right here. That lands like this right here, where this thing swings out. Of course, these things are crossing back over when this thing gets into its stowed position. And I think it's going to look something like that right there, and then this one is going to look something like that right there. Does that make sense?
Yeah, we got those grounds the same way, right? Like drawing the midpoints.
But we made some decision along the way that we want to be able to attach it to the wall without having it to be too far extended. We could have attached it over onto this side. It could be somewhere in the ceiling. Right, and hanging down off the thing to move the thing from place to place. Another one for the trash bin, to try to make something that dumps into the trash bin. This was trying to make a 78-degree output rocket with quick time ratio there. I think my intention in this one was that it got connected right here. Like these are the connection points for the quick return type of thing. So it took away that one variable about how long of this arc onto the thing was going to be. And that one, yeah, I'm not sure. I don't think I'm asking a quick return, although I think I do believe I asked a quick return in the. I think I grew to regret having done that in here. Yeah, I had design a 4-bar Grashoff crank rocker for 45 degrees output with a quick return ratio of 1.325. Was that just too many decimals? No, anyway, which I believe when I got that one. I posted the solution to this thing to this. Yeah, it came out to like 25.16 degrees, which wasn't all that pretty. I think my grading on that was kind of liberal. My recollection was it was like, oh, seemed like a good idea at the time. Things that aren't on there, I put together a bunch of statics problems. And I was working through them the other day. I didn't do all of them. So let me see which is a good one to do. Where did I start? One that I liked was the wrench. I had been looking for a wrench problem. I like that wrench problem. I think there might have been an easier way to do this, where you're trying to do, in this one, you know that there's 300 newtons here, and we want to figure out what the clamping force is going to be. One of the troubles with some of the problems is that this is actually something we haven't really dealt with is this like snap through toggle. That's actually the principle of one of these sure grips. Everybody have used this kind of wrench before? Right here, where when you clamp the thing, there's a point where they go boom, right, where you can kind of feel it, and you need to. There's usually like a little bit of an extra like little handle that's right in there, and you actually need to squeeze that to undo the toggle. But that little toggle actually makes it so that it's like it puts it on this extra little bit of squish onto the thing. But this is, and by toggle I mean that right there and that right there snap through and come back to the other position, right? It's just the lengths of these are just enough to be able to make that so that it actually kind of goes inward just a little bit, right? And this thing right here, this thing can actually go, it just fit inside that just ever so slightly. But anyway, in doing this, the most important thing is to make a free body diagram of the thing and make it as good of a drawing as that you can. And it's good to try to make it proportional and to try to spot where the places that we care about. That this right here, and then we call it this right here, and notably that this right here is a different spot than that right there. So we need to recognize some things. That you're going to have a load that gets placed right here of 300. You're going to have a force that gets aligned, and maybe I'll try to do it correct. A force that's going to be in that line right there. We can't necessarily know for sure ahead of time that it's going to be whether it's going to be this way or this way, but we know it's going to be along that line. We can see that this point is on the same line as that. Right? And I drew this poorly because this thing is below that. Okay, so we're going to have I think he's dead, force right here that we want to try to find. And so this is the F that we're trying to find out here. So what we want to do is to we'll place reactions around here. I'll call that F, B, Y. I'll just draw this as positive, and this is F, B, X. So based on this, right, so we want to take the sum of the moments about this point, about B, because, well, we'd rather not try to have to find out what that B is going to be. And So we have, looking at this right here, about this thing is going to want it to make it go counterclockwise. That's going to make it go counterclockwise as well about this point. So this thing better make it go clockwise, right? So this is going to be the FAC. It's going between A and C. So taking some of the moments about B, let's see, I have to double check something first. Okay, so we're stuck because we don't know FAC. So we need to go to another part of this. We could start looking at these other parts, but I don't think this part right here, Link, is going to help us. This is a two-force member, so we don't really need to draw this one out. But this guy right here is the key to the thing. So we notice, once again, we have to be careful with our sketch that these two things are not in line with each other. They are apart. So we draw this thing out, and maybe I'm going to make it a little exaggerated right in there. And we have a 300 that's taking place here. This guy, once again, is along this line, and this one we don't quite know what its direction is going to be. So we call this FDX and FDY. And this one, again, this needs to be in, we know that this has to be in this direction as part of compression. Okay. So this is our FAC. We need to do a little bit of geometry to be able to get this problem done. So we take a look and we see what is this angle going to be. And we see that it's going to be 30 in terms of its rise right here. And its run is 120. So I'll call it beta and say, wait a minute, I gotta be careful here. I just said the wrong thing. It's actually not 120. You have to play a little bit of a game here. We have to, see, oh no, okay, 96. Is it 96 correct? No, it's not. 96 minus, because there's 12 right here, right? So this is 96 and this is 12. So this distance from here to right here is actually going to be 84. Gotta be really careful with that geometry. So with that rise over run, that ends up being 30 over 84. And I see from my eraser mark, I got it wrong the first time and went back and went, oh, look at that. It's all screwed up. So what we do is we take the sum of the moments about D that we don't want to know. And 300 is going clockwise, so it's going to be negative 300, and that distance to here ends up being, that's 126. And so we know that this is going to be the 19.65, so we say let's just do the cosine first, so we go FAC times the cosine of 19.65, right? And that's going to be clockwise, so he too is negative. And the distance that it's going about this is 6 millimeters, which we were careful enough to exaggerate. And then in the y direction there, that's going to be positive, right? It's going to be the FAC sine of 19.65 is positive, and its distance is going to be 30. Did I get that right? Yep, 30. And so from that, we're able to find that FAC is going to be 8,518 newtons. So we can come back up to here and do a similar thing and say, so we have 300 going counterclockwise and we're going about B, so that's going to be 120 plus 12, so 132. And then we're going to have, once again, this angle right there is the 19.65 degrees. So we say that we have clockwise is the, okay, so one thing, it's in line here, so we only have to go for the sine, right? The cosine isn't going to factor into the thing. So, and that upwards part is going to be clockwise, so he's negative, and he's the 8,518, but it's the sine of 19.65, and its distance right here to B, that's the 120, and then plus this force, because he's going clockwise, counterclockwise, and that distance is going to be the 120 plus the 36 plus the 12. No, wait, excuse me, sorry, it's about B, duh. So it's actually right here, it's 36, sorry. And then we get F, and it's not, it's kind of, well, I'm a little disappointed that it's so close to that, but it's, I don't think there's anything magical about it getting so close. I don't know if I went off the board over there. I forgot. I was trying to film. I don't know if am I still recording? I am going to ask stats problems, so it'd be good to get practice on those. It's not impossible to do, though, but it's challenging. But it's like a really important mechanism skill. Any other questions on that? I think we're up at time. I hope this was useful. A little bit. Some organization. So